The universe scatters everything, so why do we create meaning? An old photograph lies on a desk. In it, young parents and a small child are smiling. The paper has begun to yellow, and the once vivid colours have faded. One day the ink may fade so much that their faces become difficult to recognise. And yet, something is strange. The physical photograph grows older, but its meaning does not necessarily diminish. Some photographs become more precious as time passes. If everything in the universe eventually disperses and decays, why do we preserve memories, form relationships, and search for meaning? Are birth, growth, aging, and death ultimately a fate imposed on us by entropy? And can the meanings and relationships we create during our lives ever be measured scientifically? Today, we will begin with the physical language of entropy and move toward life and death, memory and relationships, and the meaning of human existence. Finally, we will explore a new perspective in which information moves through time and between people as an information current, connected by what we may call an information gauge field. Entropy is often described as a measure of disorder. That is not entirely wrong, but it is not enough. A messy room and the entropy of the universe do not represent disorder in quite the same sense. Imagine placing a cup of hot coffee on your desk. As time passes, the coffee cools. Its energy has not disappeared. Heat has spread into the cup, the air, and the desk. Energy has been conserved, but energy once concentrated in one place has dispersed into the surroundings. What we never see is all that dispersed heat suddenly gathering back into the cup and making the cold coffee hot again. The laws of physics do not absolutely prohibit every microscopic version of such an event. It is simply so improbable that, in the macroscopic world, we effectively never observe it. There are overwhelmingly more molecular arrangements in which heat is distributed throughout the room than arrangements in which that heat is concentrated inside one cup. This is the heart of entropy. Entropy tells us how widely energy and matter can be distributed among the microscopic states available to a system. It is not a substance or a particle. Like energy, it is a physical quantity that describes the state of a system. But is entropy objectively real, or is it merely a subjective concept invented because human beings cannot know the position and velocity of every molecule? We do not follow every molecule individually. We describe the world using macroscopic quantities, such as temperature and pressure. The observer does have a role in deciding which microscopic distinctions to ignore. But once those conditions are defined, coffee cools and ice melts regardless of what anyone thinks about them. Entropy is neither a fiction created entirely in the mind nor a material object existing by itself like a stone. It is an objective yet emergent physical quantity that appears when enormous numbers of particles and correlations come together. The increase of entropy also reveals the direction of time. A broken glass does not spontaneously reassemble. A drop of ink spreads through water, but the dispersed ink does not gather itself back into a single point. We remember the past, but we do not remember the future. Behind all these scenes lies the entropic arrow that separates past from future. And then within this entropic universe, something extraordinary appears. Life. A human being begins as a single fertilized egg. That cell divides, its descendants take on different roles, and together they form a heart, a brain, blood vessels, and a nervous system. Eventually, tens of trillions of cells move and function as one body. Matter that was once dispersed becomes organized into astonishing order. At first glance, life seems to violate the law of increasing entropy. But a human being is not an isolated system. We eat food and breathe oxygen. We use concentrated chemical energy to build cells, maintain body temperature, and repair damaged tissue. In the process, we release heat, carbon dioxide, and waste into the environment. While creating and maintaining order inside the body, we export even more entropy to the world outside it. Life has not defeated entropy. Life is an open system that uses the flow of energy to preserve its organization for a limited time. Rather than a rock standing against a river, life is more like a whirlpool that maintains its shape for a while within the flowing water. But life is no ordinary whirlpool. It repairs itself, reproduces, remembers the past, and forms relationships with other living beings. So can entropy explain human birth, growth, aging, and death? Birth is the process by which matter and energy become organized into a self-maintaining system according to genetic information. Growth is the expansion of that organization using energy from outside. The body is damaged every moment, but it is also constantly repairing itself. It repairs DNA, removes misfolded proteins, and replaces worn-out cells. When we are young, our repair systems generally keep pace with the damage. But over time, DNA damage, altered proteins, mitochondrial decline, cellular waste, and changes in the immune system gradually accumulate. Noise also increases in the information exchanged between cells and tissues. Aging is not simply the body reaching a higher entropy number. It is the gradual failure of the balance between damage and repair. Death is also not an event that occurs when entropy reaches some predetermined value. It is the irreversible breakdown of the cycles through which the heart, brain, lungs, immune system, and other organs sustain one another. When the flows of energy and information stop, the body can no longer repair itself and begins moving toward equilibrium with its environment. Thermodynamics does not command every human being to die at 80 or 100. Extending life is not forbidden by thermodynamics. But real organisms are not perfect repair machines. Excessively stimulating regeneration may increase the risk of cancer, and repair itself always requires energy. So it is more accurate to say that death occurs not simply because entropy increases, but because a living system can no longer pay the cost of maintaining its order and information in a world where entropy continues to rise. And yet, even while we are alive, the material of our bodies is continually replaced. Many of the atoms that formed us in childhood are no longer the atoms that form us today. Still, we regard ourselves as the same person. What connects the person I was yesterday to the person I am today? Part of the answer lies in memory. Memory is the presence within the current brain and body of information about past events and environments. The smell of the house where we grew up, the nervousness of our first day at school, and phrases our parents often used may all remain as traces within our present choices. Information theory can help us estimate how much information about the past remains in the present. But the amount of memory alone is not enough. We must also consider its accuracy, persistence, accessibility, predictive usefulness, and influence on identity. Remembering a telephone number and remembering the voice of a parent who has passed away cannot be compared in the same way. The telephone number may contain more precisely encoded symbols, but the remembered voice of a parent may shape a person's emotions, choices, relationships, and identity for decades. This is where the quantity of information and the meaning of information begin to separate. Information theory can tell us how unexpected a message is and how many bits are required to store it. But the same information may have completely different meanings depending on who receives it. The short sentence, "It will rain tomorrow," may be crucial to a child preparing for a picnic. To someone confined to a windowless hospital room, the same sentence may change almost nothing. How then could science approach meaning? One possible method is to ask what actually changes when a piece of information is removed or disrupted. If losing that information reduces the probability of survival, worsens predictions, or impairs the ability to achieve a goal, then we can say that the information has operational meaning for that system. An old photograph may contain very little digital data, but if losing it profoundly alters someone's connection to family history, memory, and emotion, then that photograph may possess great semantic value. There is, however, a clear limit. To measure meaning, science must first specify a criterion such as survival, prediction, or goal achievement. We may measure some of the effects that information has on behavior, but we cannot reduce the full value of a human being to a number. What we measure is an effect left by meaning, not the whole of meaning itself. Now imagine information moving through life and relationships. Our senses become neural signals that travel into the brain. Memories from the past flow into decisions made in the present. Language and habits pass from parents to children, while the knowledge of one generation passes to the next. We may describe this flow as an information current. But advertisements, rumours, and noise can also transmit enormous amounts of information, so we may distinguish from the total information current a semantic current, the part that actually changes survival, goals, identity, relationships, or the future of a system. If an information current is the total flow of information through a life, a semantic current is the portion of that flow that genuinely changes where the life goes next. Yet information does not always preserve the same meaning as it moves. Even members of the same family may remember a shared event differently. What a parent remembers as a decision made to protect the family may remain in a child's memory as the moment no one listened. Neither side must be lying. They remember the event from different informational frames, shaped by position, emotion, and expectation. In physics, gauge theory provides a way to connect standards used at different locations so that physical quantities can be compared consistently. If we apply this idea to information, we can imagine a rule that connects meaning across different times, people, memories, and contexts. This is the basic intuition behind an information gauge field. Translation between languages offers a useful analogy. Replacing each word according to a dictionary does not guarantee that meaning has been preserved. We must also consider culture, situation, relationships, facial expression, and the speaker's intention. An information gauge field would act like a rule for transporting a frame of meaning from one context to another. But an important distinction must be made. An information gauge field has not been established as a new force of nature. Whether it corresponds to a physical field in space-time or serves only as an effective mathematical tool for describing memory and information processing must be decided through experiments and data. From this perspective, one particularly interesting idea is the holonomy of memory. Imagine that an event is experienced, stored as a memory and recalled many years later. We begin with the experience, move through storage and forgetting, then through recall and reinterpretation, and finally return to the same event. The event at the beginning and the event recalled at the end may be the same, but its meaning may not be. When we revisit our childhood home decades later, the alley and the front gate may still be there, but the person looking at them has changed. We may finally understand a decision our parents made that we could not understand as children. The change that remains after information has travelled through several contexts and returned to its starting point may be described as an information holonomy. If the holonomy is small, the experience and the recalled memory have remained relatively consistent despite passing through several stages. If it is large, the memory may have been reconstructed, or its meaning may have changed significantly. But a large holonomy does not necessarily mean that the memory is wrong. Seeing an old wound from a new perspective, or finally forgiving someone we once hated, also changes the meaning of the past. Memory is not a warehouse in which the past is stored unchanged. It is a continuing relationship between the person we are now and the past we are trying to understand. Relationships behave in a similar way. When a story passes from one person to another, moves through several people, and finally returns to the first speaker, it often comes back changed. This is not merely because some words were lost. The story has passed through each person's experience and emotion, trust and conflict, acquiring new interpretations along the way. The degree to which the outcome depends on the path taken may be described as information curvature. If meaning remains similar along different paths, the curvature is small. If interpretation changes dramatically, depending on the path, the curvature is large. But a relationship with high curvature is not necessarily a bad relationship. Love, growth, art, and forgiveness can all transform interpretation. Information curvature would not be a moral score of good and evil. It would be a candidate measure of how much information changes as it moves through relationships and contexts. We do not return unchanged after forming relationships. Perhaps loving someone means allowing their existence to alter the path of our own life. Beautiful metaphors, however, are not enough to make a scientific theory. If the information gauge perspective is to become a genuine theory, it must predict something that existing information theory cannot. For example, we could test whether memories matched in information content and accuracy change more over time when their holonomy is larger. In artificial intelligence agents performing long-term tasks, we could test whether accumulated information curvature predicts goal drift or contradiction before conventional measures do. If mutual information, transfer entropy, and ordinary network analysis already explain all the results, then the information gauge field may remain only a different mathematical language for existing ideas. Science requires more than a new name. It requires a new prediction. Now let us return to our original question. Why must human beings be born, grow, and eventually die? Entropy helps explain why life requires energy, why the body must be continually repaired, and why damaged order does not spontaneously restore itself. But entropy cannot answer the question, what was I born for? Physics explains the conditions that make life possible. It does not command the purpose of a life. A reason for existence is not a physical quantity that can be read from a thermometer or an entropy meter. Still, the information gauge perspective offers at least one intriguing way to look at the question. A human being is not an isolated point, but a node connected to countless memories and relationships. Even after someone dies, their words and habits, knowledge and love may remain within the memories and choices of others. This does not mean that personal consciousness is physically preserved forever, nor should we use the persistence of information to deny the reality of death. It means only that the causal changes created by one life may continue to act within the paths of other lives. Entropy tells us that our bodies and forms cannot last forever, but entropy alone does not determine how our finite existence will alter the lives of others. Let us look once more at the photograph on the desk. The paper is aging and its colours are fading. One day, even the person who remembers the photograph will be gone. Physical structures do not last forever, but if someone looks at that photograph and comes to understand a parent, speaks more gently to a child, or decides to resolve an old conflict, then the information in the photograph has flowed into a choice made in the present. A relationship from the past has passed through the present and changed the path of the future. We cannot stop the entropy of the universe. Our bodies age, our memories change, and one day the flow that sustains life will come to an end. But perhaps life is more than remaining in a state of low entropy. We remember the words of others. We pass our experiences to the next generation, and we leave irreversible traces in one another's time. Perhaps the meaning of existence does not lie in remaining unchanged forever, but in what information we preserve during our finite time, what relationships we create, and how we alter the paths of other beings. The universe scatters everything, but within that scattering time, living beings remember one another, if only for a while. This has been ThothSaem Physics.